from what we know as the boundary work. So problem statement is as we have the internal energy change, which is 84 plus 3.56 p nu, is the equation for some substance in a container where U is the kilojoules per kilogram, P is kilopascals, nu is meter cubes per kilogram, and the system with a mass of 3 kg expands from 500 kilopascals to a volume of 0.25 meter cubes in 100 kilopascal. Process happens in a fashion that P nu to the power of 1.2 is constant. These processes where you have P nu to the power of some value constant, not this one, but generally, P nu to the power of n constant. These processes are called polytropic processes. Why it is polytropic? Because the poly means that multiple of directions. Tropic means directions, because you can change the value of the n. With that change of value of the n, you can get different, the directions for the boundary work. So you can have P nu n is 1, it means isothermal. You can have P nu to the power of k, which is 1.4. You will have that adiabatic reversible work. Because so different works, different directions, therefore it is called polytropic. Now let's solve the problem. So we have a container. This is the U of the container, and the system expands. So that, let me show the process. This is the container, and there's an expansion work. As it expands, you will have that change of pressure, which is P1, which is 500 kilopascal, and then P2 is 100 kilopascal, the pressure drops, and the volume 2 is also 0.21 meters cube, and the mass is 3 kilograms. The question says find delta U and the W and the Q for the process. Okay, now let's solve it. Firstly, I will write the first law for the process. The first law for the process says that the first law. It says that the change of internal energy of the system is equal to the total in minus total out. Okay, and for our process, there is actually, let me see, what do we have here? We have that expansion process, and expansion is work out. Okay, expansion process is work out, and since we have expansion process, that there should be a heat transfer into the system. There should be Q in. Okay. This one should be equal to delta U. Okay, now let's find the first work out. That will be equal to P dP. Okay, or you can write this one as the mass, and out of the brackets you will have P d nu. Okay. And the pressure and the volume relationship is important here. The question says P nu to the 1.2 is constant. You can find this constant value here. So if I know that P2 nu to 1.2 is constant, P2 is 100 kilopascal times 10 to the power of 3 multiplied with nu2 is V2 by M. So it will be 0.21 divided by 3, it will be 0.07. And this one multiplied with 0.07 to the power of 3, it will be the constant. Now who can tell me the value of the constant here? So what will be the value of the constant? So from that value of the constant, I will be able to find the P d nu work. Let's see, 0.07 to the power of 34.3, Rajab says 34.3, and now comes this boundary work, and to find that boundary work, I need to know the relation between P and the nu. To get that relationship, I know that P nu to the power of 1.2 is constant. Instead of P, I can write C divided by or multiplied with nu to the power of negative 1.2 instead of P. And I can integrate that quantity, so P d nu, nu1 to nu2. That one will be equal to nu1 to nu2, and the C nu negative 1.2, and d nu. And you know the derivative, the integral of x dx. Okay, the integral of that one means x 1 plus 1 divided by 1 plus 1. Similarly here, c nu negative 1.2 plus 1.2 divided by 1.2 plus 1. Okay. This one multiplied with c value, and you get from nu1 the nu2. And I know that nu2 value is 0.07, but nu1 value is unknown. Who can tell me how can I find the nu1 value? How can I find the nu1 value? I know nu2 value, it's okay, but I don't know nu1 value. How can I find the nu1? So let's see, what are your ideas? What are your ideas? How can I find it? Okay, so we can find the nu1 value. Let me show you how can you find the nu1 value here. So that no, Rajab, it is not. So I know that P1 nu1 to the power of 1.2 is same as P2 nu2 to the power of 1.2. And I know that P2 is 100 kilopascal times 10 to the power of 3. Nu2 is 0.01. P1 is 500 10 to the power of 3. And I can find nu1 to the power of 1.2, or instead you can find the nu1 itself. Instead of that one, you can find the nu1. So what is the value of the nu1? So you have only one unknown. P1 is there. So only unknown will be nu1. And if you know the nu1, then we will find the boundary work. And the first 0.014 says Mehmet Tağlı meter cubes per kilogram. So therefore, that nu1 value from here, it will be equal to 0.04. Okay? And I know that C value, which is 34.3, and therefore I can find this relationship here, and it will be divided by negative, what is that, 0.2, it's okay, multiplied with that 0.014, sorry, it should be nu2 minus nu1, it will be 0.07 to the power of negative 0.2 minus 0.014 to the power of negative 0.2, and that will be equal to the boundary work that we should do. So that is the boundary work that you are going to do to find the PD near. Actually, I didn't calculate the mass. Yes, at the end I will multiply with the mass, and I will get that PDV. PDV is just mass multiplied with PD nu, and then you can find that PDV work. Nice. Let's see. So Mehmet Tağlı 11. So 111.16, and Rajab says 110.84. So I have two answers here, but let's make it as 111 so that nobody has a problem. Because there are two different answers. So 111 joules for the boundary work. But this one is not joule, this is joules by kilogram. Okay, but what I need is that joule. So what I will do now is that work out is m into PD nu. I have found that part. Okay, the rest is not so difficult. Just you will multiply with the mass, and mass is 3 kilograms, and then 3 times 101, you will get 303 joules. Okay. But this one is negative. Final result is positive, actually not negative. But this one is positive, 333 joules, so I have found that one. You see, the first one is okay. Now comes that Q or delta U. Q is, so I may ask this question for you. Can I find Q or delta U? Which one is possible to find firstly? Should I find delta U and then Q in, or should I find Q in then delta U? Who has any idea which one should come first, delta U or Q in? Let's see. Which one? Yes, there is one answer, that is delta U. Ali, yes, you are right. So now let me find that delta U. U is 84 plus 3.56 P nu, and therefore U2 minus U1. This one is the equation for the internal energy. So it will be equal to 84 plus 3.56 into P nu minus 84 plus 3.56 P nu. Okay. This will be P2 nu2 and the P1 nu. And this one cancels out, no problem. And the 3.56 multiplied with P2 is 100 kilopascal, 100 times 10 to the power of 3 multiplied with nu, which is 0.07, minus 500 times 10 to the power of 3 multiplied with 0.014. Okay. From here, you will get the value for delta U. Ali, Muhammad, Rajab, yes, you are all right. From here, you will get that delta U value, and then you can tell me the value of delta U, and then we will find the value of Q in, and the first part of the question ends. So you've come to 0. Okay, good. It's not n. So the delta U has become 0. We have 0 delta U. This one is joules by Coulomb. Joules, actually, not joules by Coulomb. So it means that the process happened as a fashion that, so let me write it as here, 0 is equal to Q in minus that work out, and from here, Q in is equal to work out, and that is equal to 333 joules. So what it means is that all heat is used for work. Okay. All of the heat that is given into the system is used for the work, the boundary change. It is not added there is no internal energy change. That's here. If the same expansion occurs as in the question, but with 30 kilojoules of heat transfer, what will be the value of the work transfer? If the same expansion happens, but this one is very easy part of the question, no need to care about it. But with 30 kilojoules of heat transfer, what will be the value of the work transfer? And in that case, you will have that 30 kilojoules of, that is, heat transfer. Let me ask this question actually for you. So what is the answer for the B part? It is not so difficult question. It is very easy one, but you can tell me the value for the B part. So what is the okay, so what do you think the answer will be when the value is the 30 kilojoules? So what is your result? What happens? So it is not so easy, difficult question. The result will be the same, because since you have delta U as 0, so it means that whatever Q in is there, it should be equal to work out. If it is 30 kilojoules, it should be, that is 30 kilojoules. If it is 20, it will be 20, because all of the heat is used for the work. Therefore, no need to care about the B part. That is the same. Y values in A, B work transfer are different. Okay, so it should be not Y values, but it should be are the values between work and the A and the B are different. So for the A part, you will have that heat transfer 30 kilojoules. So that will be, it is only due to amount of the heat transfer. Here you will have that is 330 joules of heat, and that is used for work. And here you have 30 kilojoules of heat that is used for the work. There is any calculation error in your results, then the question is this way. If you have any calculation error, I don't know, that will be your problem. Yeah, but if there is any calculation error, the values are due to the amount of the heat transfer added to the heat container. Okay. Good. Now let's go to the next question here. The question says that air at 400 Kelvin is heated to 800 Kelvin at constant pressure. Find enthalpy and internal energy change per unit mass using table A17, table A2C, corresponding specific heat value to average temperature value and average specific value. Okay. Now let's go to the table and find those results here. I will go to table. Let me share the screen with you. So you can see. This is the question. First, I should go to table A17. So if you go back to the back of the tables here, you can see that A17 is ideal gas properties of air. So I will go to that A17 here. Let me do that for you. A17. So it says that find the enthalpy change and the internal energy change. So firstly, I will find the delta U. Delta U will be U at 800 Kelvin minus U at 400 Kelvin. Okay. And U at 800 Kelvin is 592.30. 592.30. That is U for 800 Kelvin. You can see this is 800 Kelvin, and this is the U value. And the U for 400 Kelvin is, let me go back to the 400 Kelvin. This 286.16. Okay. This 286.16. And from here, you can tell me the value of the U. And similarly, I'm going to find the value of enthalpy change. It will be enthalpy at 800 Kelvin minus the enthalpy at 400 Kelvin. Okay. And I will take the similar values here, and 800 Kelvin enthalpy is 821.95 minus at 400 Kelvin, it is 498. 498. Okay. So you can tell me the values of this. For the first one, Matawa says that 306.14 kilojoules per kilogram. This is for internal energy change. Second one, 4020 and 97 kilojoules per kilogram. This is for the enthalpy change. Now comes the question says that use table A2C. Okay, let's go back to the table A2 and the C. Let's see what is waiting for us in that table. A2 and the C. For that table, that we have only the CP value, which is given as A plus BT plus CT squared plus DT to the power of 3. And there is a bar here. It means that it is per unit mole. Okay, at the end, we should convert into, so let me write table A2C here. And for that table, CP over bar. Over bar means that you have a unit of per unit kilomole. Okay, so kilomole into Kelvin. Okay, what you can do is that you can multiply it with the that is inverse of actually molar mass. Okay, that molar mass has a unit of kilogram per kilomole. Okay, and if I multiply with the CP bar with the inverse of 1 by molar mass, and you will get the Cp that we know with the unit of kilojoules per kilogram Kelvin. Okay. This is the Cp value. And the question gives us Cp, which is A plus Bt plus Ct squared plus dt to the power of 3. What it means? It means that this Cp value, okay, versus temperature, it follows some relationship that we don't know it. But for example, I don't know, but let me assume that this follows a relationship something like this one. For example, this is for air. It can be that for other substance, let me use different color here. Okay, this is fluid 2. Okay, and instead of air, let me write as fluid 1 because it's not fluid 1. It will be fluid 1. Okay. Now the question is fluid 1 and the fluid 2. For fluid 1, what is the value of the D? Can you tell me? For fluid 1, what is the value of D? This value of D, it is parabola. You can see it is parabola. If it is parabola, then the value of the D will be, you can tell it. These are examples, okay, examples. It will be 0. If it is fluid 2, it is a linear change. You can see it is linear change. But this one is parabola. Okay. And linearly changed, therefore, that the C value will be 0 and the D value will be 0. Okay. And the A and the B values, these are by experiment. Okay, so by experiment, and this is also by experiment. But in experiment, it is not a curve, but in experiment, you have got something like this one. Let me show in experiment way. Okay. In experiment, what you are getting is that, so this is first experiment, second experiment, and the third one more experiment. So you see, you've got different experiments. And when you look at the values and you assume that this one should be parabola. This is what you assume, and you try to find the best parabola. It is not always the, you're trying to find the best parabola. Okay, this is called the curve fit. Similarly for the fluid 2, and the fluid 2, you are doing the experiment, and you find that for the first point it is here, and it is here, then it is here, and it is here. So you can see for the second point, you have fluid 2. These are your experiments, and you assume that this should have a curve fit that is linear. You can see it is not the perfect linear. Okay, and this one is the linear curve fit. Okay. Now they have done experiment on different fluids and find this Cp value here. Okay. For air, for example, they have done the CP experiment, and the Cp value is this one, and the A is 25.48, and the B is this one, C is this one, and D is that one. Okay, and that it is valid in this temperature range with an error of 1.19, and this is the average value. Okay, this is the maximum error, this is the average error. Good. Now what I will do is that I will find, so the table only gives the enthalpy, therefore I cannot find the internal energy. So what I will do is that I will say that dH bar is equal to that Cp bar into dt. And or you can say that H bar means that it is per unit mole. This one means that kilojoules per kilomole. Okay. Or joules per kilomole. It doesn't matter, then it's per mole unit. You will integrate from 400 Kelvin to 800 Kelvin. Okay. And Cp dt. And instead of that Cp, you will write 800 Kelvin. And instead of that Cp, you will write that A plus Bt plus Ct squared plus dt to the power of 3 and dt. Okay. And you will get this A and the B and the C D values from the chart. or you can integrate it AT plus BT squared by 2 plus CT to the power of 3 divided by 3 and DT to the power of 4 plus divided by 4. And you get from 400 800. And you get the value of it and find. And then this one will be that H bar. What you will do is that you will get the delta H. This one is actually delta H. To get the delta H, what you will do is that you should divide delta H bar with the molar mass of air. And that will be that delta H bar divided by molar mass of air is 29 kilomole per kilogram. No, actually it is opposite. You see, that is opposite. Kilogram per kilomole. Okay. Good. Do you have any questions for this one? Is there any question? No. Good. Now comes that we have found the A2C part and corresponding specific heat value to average temperature value. This is the method C. Now let's do that one. So that part C. So I should find the corresponding specific heat value to average temperature value. Average temperature is 400 plus 800 and divide by 2. It makes 600 Kelvin. Okay. And I should find the CV to T average. I should find CP to T average. Okay. And then what I will do is that delta U will be equal to approximately CV into delta T, and delta H will be equal to approximately CP into delta T. That one will be CV, and that one will be CP. Let's find it now. And for that one, I will go to the table A2. Okay, this one is table A2. For table A2 and the B, this one is the B. For 400 now, for 600 Kelvin, CP and the CV value for air. You can see it is air. I'm looking for CP and the CV for that temperature. CP is 1.0151 kilojoule per kilogram Kelvin, and the CV value is 0.764 kilojoules per kilogram Kelvin. Okay. And then from here, you can find that the result here, it will be 0.764 multiplied with 800 minus 400. That one will be equal to 1.051 multiplied with 800 minus 400. Okay. So tell me the result, please, if you have it. So then we can compare our result with the previous one. You see what are your values, and then we'll compare the values with the previous one. Now for the B part, I've not done it, but it takes lots of time. I don't have that time for calculating the values here. But for the C part, you can do it easily. It is very easy one. So that 3, let me write it, 05.6 kilojoules kilogram. The second one is 420.4 kilojoules per kilogram. You can see it. So it is not so different. You can see it is almost the same. The error is small. The D part says that use average specific value. There are lots of methods, and D part says that use CV average. CV average will be equal to CV at 400 Kelvin plus CV at 800 Kelvin divided by 2. And the CP average will be CP at 400 Kelvin plus CP at 800 Kelvin and divide by 2. Okay. Now let's solve it. CV at 400 Kelvin is, first let's start from CP, 1.13 and 1.099. 1.13, 1.099 divided by 2. For this one is for actually CP. Another CP and the CP, and here you have CV, and this one is also CV. For the CV values, you will have that 0.726, 0.812, 0.726, 0.812 divided by 2. This one and that one. So therefore, delta H will be equal to approximate. These are approximate, okay? These are not exactly. Cp average into delta T, and delta U will be approximately Cv average into delta T. Okay. Now you can tell me the values of that. This one will be again the 400 multiplied with, and this one multiplied with the 400. You can actually do all of the calculations, and let's write the final result and finish this example. .1.056. Next one was 0.769. Just multiply those values with 400, and you'll get 1.0566, 0.769. Okay, this one you'll get with, you have the value as a result 422.4. The second one is 307.6, and this one is kilojoules per kilogram. This one is kilojoules per kilogram. Okay, so this is the first last method. You can see that we have got the values are very close. It is not so, there is error, but it's not so large. But if you consider that 2 plus minus with respect to 400, it's not too much. Okay, so you can see there are different methods to calculate this, the enthalpy and the internal energy change of the fluid. And you can do it with any of the methods here, and you will get approximately similar values. Good. Okay, now comes the open. You got the open systems. Okay, when we say that open system, there are different open systems, and we will talk about mostly steady flow devices. Okay, steady flow devices means that no change with respect to time. There are different range of the steady flow devices. Some of them I don't even know what is that. Some of them which are very famous and used everywhere. For example, you have the boiler, and it is used to bring substance to a vapor state. And for that boiler, the work is 0, and the P is constant. You can see that this is a very good chart. Okay, it gives the values which are 0. These are 0 for example, any. If it is given as 0, for example, condenser, work is 0, pressure is constant. Okay, and the one more important thing about these devices is that if it is heat exchanger, then the pressure will be constant. For example, this one is heat exchanger, the pressure is constant. This one is heat exchanger, pressure is constant. You can see whenever pressure is constant, it is mostly the heat exchanger. Okay. And we have also diffuser. So that diffuser is something like this one. You have the increase of area. This is diffuser. Okay. It is opposite to the decrease, the conversion part of the pipe section venturi. It converts the kinetic energy to higher pressure values. Work is 0, Q is 0. Or evaporator, bring a substance to vapor state. Work is 0 and the P is constant. Feed water heater. It is used for Rankine cycle, the electricity generators. So work is 0 and the P is constant. Or flash evaporator. This is used in refrigerators. Work is 0 and the Q is 0. But you can have any of the devices, for example, intercooler used in compressors. So the work is 0 and the P is constant. Because it is heat exchanger, it is used to cool the compressor fluid. And therefore, it is the heat exchanger. Economizer, for example, this was heat exchanger. So you can see the work is 0, you can see P is constant. The aerator, okay, it is used to remove the air. You can see that part, air. But generally dissolved gases, so work is 0, P is constant. So mixing chamber, pump, that is reactor, regenerator, steam generator, supercharger, turbocharger. You can see the diesel engines, for example. These are used in valve, for example, the flow restrictor. Okay. P drops and the work is 0, Q is 0. So this is a very good chart. If we will do examples for not all of the devices here, but we will try to as much as possible, and we will try to solve examples as much as possible about most of the devices here, so that you can have an idea what is it like. Okay. And there is a simple example here. There is a vessel, and the water flows into an empty vessel at a constant mass flow rate of 7 kilograms per second. This one is 7 kilograms per second. And then water exits at 1.4 L. So this one is 1.4 L. Okay. And then L is the instantaneous change of the fluid layer. You can see that fluid layer changes, and the exceeding fluid flow is proportional to that one, which is 1.48. Area of the base is 0.4 meters squared, 0.2. And density of water is constant with value of 1000 kilograms per meter squared. Find the relation between height and the time. So how the L change, it asks for how L change with time. Okay, now let's solve it. So what I will do is that I will take my system as this is my control volume. Okay, you can see the dashed lines here. Okay, this is the control volume. Into that control volume, there is fluid enters. There is fluid that leaves the control volume. Okay, and due to that addition of that is water to that control volume inside, so let me write it one by one. So this is that my control volume. Okay, the mass change here. Okay, and there is mass into my system, and there is mass out of my system. Okay, and therefore mass change, the change of mass dm with respect to dt inside system, or CV. Change of mass with respect to time inside that control volume will be equal to the total mass into that system minus total mass, the mass flow rate, mass per unit time into that system minus mass flow rate out of that system. This will be the equation that I'm going to solve. Okay. This is very important. This one will give you an important result. And the dm by dt of the system, and I can write the mass of the system as that rho into that volume. The mass of not system, but water, let's say. Mass of water, this one is not system here. This one will be m of water inside CV. System here is open system, so this one let's put as open system. So it will be rho into volume. Okay, and instead of volume, I can write rho, and I can write that area, which is this one. I can write that L. Okay, and therefore that dm by dt, that one of CV control volume, will be equal to that d by dt of rho into A into L. Rho and the area is constants, therefore I can take it out of the brackets, and you will have dl by dt. Okay. This one will be equal to m dot in minus m dot out. Let's write that equation. Rho A dl by dt will be equal to m dot in minus m dot out. This is a money balance, you can say. You have some money into your system, money out of your system. As a result, the money inside the system changes. Mass flow rate into the system is 7, and out of the system is 1.48. And therefore, you will have that rho into area and the dl by dt will be equal to 7 minus 1.4 F. And from that one, I will use the famous integral rule, which says that you can separate and then you can integrate. This is a very famous integral rule. that you can always use. I first separate, which is dl by 7 minus 1.4l. Okay, that one will be equal to, that is 1 divided by rho a. Okay, that is my integral. And from that integrals, you know that 1 by x dx is ln x. Okay, or so if with that similarity, you can get the integral of this one. And to get it, first I should integrate. I will integrate it, and I will integrate dt. There is also dt here. I forgot to add it. So that when time is 0, so is there any fluid? Oh, let's say that at time is 0, there is no any fluid. Then time is t, and there is a length of L. This is the expression. So we can say middle left-hand side. What is that left-hand side equal to? First, let me share only the screen, just 1 minute. So share only the presentation whenever I change the screens, that you are not distracted. Okay, who can tell me the left-hand side? What is the integral of the left-hand side? It is a simple function, but you can tell me the value, the result of that function. Is there any ideas? So L by ln 7 minus 4 point L. ln L into ln. So ln part you are right. Let me write the parts that you are right, and then we can discuss the rest. So it is true that it will be ln 7 minus 4.1L. Okay, this is the part. But if you take the derivative of this one, so let's take derivative of that one here. So ln, instead of 7 minus 4L, I can write ln u. It will be that derivative of complex function is that you take derivative of this one and derivative of that one. Therefore, you will be 1 by u and divide by, multiply with du by dl. Okay. If you do that for our case, it will be 1 by 7 minus 4.1.4L multiplied with derivative of that one with respect to L, negative 1.4. So you have this part missing. Multiply with negative 1 by L. No, of course, no. So I should divide by this term as negative 1.4. Okay. So this is the left-hand side, and I will integrate from 0 to L. And the right-hand side, of course, will be equal to time divided by rho into area. Okay. Now let's finish the left-hand side. For the left-hand side, you will have that ln, you will have 7 minus 4.1.4L divided by 7 will be equal to, for the right-hand side, the only variable is time. Therefore, what I can do is that I can say this as constant C. Actually, not that one, but overall, because that I don't want to divide something with C. I can say that 1 by this term. This one is the C, constant. And there is one more constant here. Let's say this one is C1. This one will be equal to negative 1.4 multiplied with C1 and multiplied with T. Therefore, negative C2 into T. That is the right-hand side. Okay, now let me add just one more slide here. Okay, now this one's okay. Let me add right here. And then finish it. So if I exponentiate both sides, you will have that 7 minus 1.4L will be equal to 7 times exponentiate of negative C2 into the T. Okay, and then you will have that value will be equal to 7 times 1 minus e negative C2 multiplied with T. Okay, this one there, and divide by 1.4. It will be L. As a result, L will be equal to 5 times 1 minus e negative C2 time of T. Okay, so if there are any questions, you can tell. But this is the final result. If you have any questions, you can tell me. Okay, so let me ask you this question. So if time is large, so what will happen to this function if time is large? What will happen to that function? So you can tell me that it will be 5. Alex says it will be 5. Yes, you are right, Alex. It will be 5. So that 5 meters. So when time is 0, so that t is 0, this function makes as 0. So t as 0 and L makes e to the power of 0 makes 1, and 1 minus 1 makes 0, and this one is 0. When time is 0, L is 0. We have said it. It is our condition. Time is 0, L is 0. It should be. I've imposed it. Otherwise, I cannot solve it. When time is large, it becomes 5. If I draw it, so I will draw in next question here, or let me add one more slide. We are running out of space here. I will add one more slide here. So why do we do that? You will see the importance of the steady flow devices. Okay. Now let me present a window. Okay. So my function was L was 5 times 1 minus e to the power of negative c 30. And therefore, my graph of L versus time, t, okay, will be equal to, when the time is 0, the L value is 0. When the time is very large, L becomes 5. Okay. And therefore, the function should be something like this one. Okay, but after very large time, it will not change. It will not be exactly the same as 5, but it will asymptotically approach it. Okay, let me a bit slower rate, faster rate actually. Okay, well, the last part is not true, but it should be something like this one. You can see that now, till that part, this one, you have that unsteady or transient L. But from this part on, okay, L is independent of time. Okay. For example, if I select the time as, let me show one example. If I select the time as this one, I will have the same L. If I select time as this one, I will have the same L. If I select the time as this one, I will have the same L. You see that the L value doesn't change with respect to time. It is independent of time or steady. You can see the difference now. If you fill the container with this proportion, after some time, it can be, for example, 10 minutes. It can be 15 minutes. The L here will not change. It will be constant. You see, it is beauty of the exponential function. So it is very similar to, that is there any similar example here? That sensors, there are examples for the sensors, but let's not make our problem complicated. But here you can see that after some time, the container flow will not affect the container. It says that. So after some time, container L, it will not be affected by flow. It will be constant. This is what we call as steady. If you go back to here, you see the devices. All of these devices are steady. Steady means that they are not steady. The transient effects have died out. So you are looking for that part. Okay? For example, when you turn on pump, so turn on When you turn on pump, first it is transient. Okay, but after some time, it is steady. Okay, for example, if you are looking for, let me, P inlet, outlet, for example, outlet pressure of the pump with respect to time. At the beginning, you can have something like this one, but then it will be constant. Or even it can be something like this one, then it will be constant. It can be something like this one, then it will be constant. You see, these parts that we are looking for is the part that we are analyzing in thermodynamics. Good. If you have any questions, you can ask. No? Good. So there is a mixing chamber here. The hot water at 60 degrees Celsius is mixed with cold water at 20 degrees Celsius. In an ordinary shower. This is the shower, ordinary. It is not a rich man's shower, but it is ordinary. It can be found at any house. It is desired to supply a 45 degrees Celsius of water at a steady rate. See, it is steady. If the pressure is 1.5 bars, find the ratio of mass flow rate of hot water to cold water. It is a very funny example. Nobody needs it. Okay, good. Let's solve it now. So what we will do here, my dear friends, pressure is 1.5 bars. It is constant then, yeah? So here you have 1.5 bar. Here you have 1.5 bar. I assume that pressure is constant, otherwise they are playing with our feelings. Find the ratio of mass flow rate of hot water to cold water. This is a very good question, actually. So now let's solve it. So my first question comes to that, is it open system or closed system? Is it open or closed system? My friends, it is closed. It says, is it open or closed? Ruslan, open. Open. Ali Saif, open. Yes, of course it is open system. There is mass flow rate. You can see hot water comes, cold water comes, and they are mixed, and you have the good shower in the bathroom. Okay, these are open systems. If it is closed system, then how can you have a shower? So let's solve our problem then. Hot water at 60 degrees Celsius. So this one is that. First, I should select my control volume. Okay. My control volume is, you will not believe, but it is the shower itself. Okay. This is my control volume. The red color. Red, red, red. So this is my control volume. Okay. That control volume, I have inlet. I have again inlet, but this one is 2, this one is 1, and I have outlet, which is 3. And of course, it is steady, always. Okay, in thermodynamics, when you say a device is unsteady, that means meant that you cannot solve it. Okay, you are in trouble. The steady means that in same as out. That is the beauty of the steady. Okay. And let's write it as firstly conservation of mass. Conservation of mass means that m dot 1 plus m dot 2, 1 plus 2, will be the same as m dot 3. This is the conservation of mass. Now comes the conservation of energy, or the first law. Okay, and the first law says that again the in is same as the out. Okay, and for the open systems, let me write it. But so if you remember, we have said that we can have the mass energy transfer by mass, which will be equal to U plus P by rho plus V squared by 2G plus Z. Okay, you can have that Q in, and you have that work in. Okay. For this system, there is no work. For this system, we are assuming that it is adiabatic. Q in is 0, adiabatic system. Okay. Okay, and then you will have these terms here. Velocity and the potential energy on thermodynamics is not so important. Therefore, you will have that U plus P by rho. But in thermodynamics, we are not writing U plus P by rho, but we're writing it as enthalpy. Okay. This one is in thermodynamics. This one is in fluid mechanics. When it is in fluid mechanics, pressure itself is important. But when you are in thermodynamics, the combination property is important. Okay. Therefore, you will have, if you write the conservation of energy, you will have that m dot 1, enthalpy 1. This one is always open system. Okay. Always in open system. Plus that m dot 2, enthalpy 2, will be equal to m dot 3, enthalpy 3. And if you remember, we have said that for incompressible substances, we can write that enthalpy as Cp into T. Okay. And therefore, I can write this one as m dot 1, Cp and temperature 1. Or you can write this one as Cv into T, or you can write C. Doesn't matter. It will be equal to m dot 2, Cp into T2 will be equal to m dot 3, Cp into temperature 3. And now you have that beauty. Cp cancels out, Cp cancels out. The question says that T1 is hot water is 60. T2 is cold water is 20. Mixture is 45. Okay. So that 60 m dot 1 plus 20 m dot 2 is 45 m dot 3. Okay. And also I know from here that m dot 1 plus m dot 2 is equal to m dot 3. Okay. So you have how many unknowns? You have, how many unknowns do you have? How many unknowns do you have? How many? 3 unknowns. How many equations do I have? 3 unknowns. And I have 2 equations. You see, that is called undetermined system. So underspecified, actually, you can also call it indeterminate or undetermined. Nobody knows it. Good. So now what is the question says? Ratio of mass flow rate of hot to cold water. The question is interested about the ratio. It says that what is m dot 2 divided by m dot 1. I can call it as this ratio as R. This one as R. You can divide all of the terms as, you can also, you can simplify it here. It can be simplified by 5. It will be 4. It will be 9. It will be 12. Okay, even by 3, it will be 4. No, it is not possible. 12 is good, and 12. Okay, so that you can subtract it from that one. No, it will not help. You cannot actually multiply with 9 here. Let's multiply it with 9. You will have 9 here, you will have 9 here, you will have 9 here. This one subtracted with that one, you will have the zeros here. This one goes to 0. You will have that 3m dot 1 plus minus 5m dot 2 will be equal to 0. And from here, m dot 2 divided by m dot 1 is equal to R, and that one will be equal to 3.5. That's the ratio. So we have solved this question too. I think, yes, we have finished it. There is one more question, but let's see, do we have time? No, I stopped the recording now.